you actually are. Probably going to do it again with these things here. Let's take a look. There we are. So let's do this pretty quickly. I increase this. Does it shift to the left or the right? Left. This one. I decrease it, shifts towards it. This one, same thing. Left and then right. Okay. Good. Just walk through those slides. Let's move on. Unless, is everybody okay with this, I think, right? If not, please ask. I don't mean to move faster if I think that it's difficult, but if I think you guys all get it, then I'm going to want to move through this. Okay. So now, the concentrations are pretty easy to see, I think, right? That's something that visually and intuitively should make sense. But the other two may or may not, depending on how you think. So what were the other two different conditions that I could apply as stresses to an equilibrium system, and therefore applying Le Chatelier's principle, see the adjustment? Temperature, and pressure. So we're going to look at pressure, and then I'm assuming the slides will lead us to temperature next. Okay. So when looking at pressure, we're looking at the reactant side and the product side of a balanced equilibrium. Okay. And if I'm, sometimes I put up things that are obvious, but then again, I look at it, first thing I kind of laugh to myself, second thing is, actually maybe that's good because maybe that's something that's not so obvious. If you have that, you must have a gas on one side or the other. If you're looking at pressure, you're dealing with gases. So you must have a gas, at least one, on one side of the equilibrium. That's what this is telling you. If you care about pressure as a potential adjustment in an equilibrium. Makes sense, right? If I have a solid or a liquid, what difference would that make? Even aqueous. Adding the pressure is not going to change much. But gases will. So I have to have a gas in either the reactants and or the products. The second thing is, can the amount, so there, if I have constant volume and I have the same number of moles of different gases, what does that do to the pressure? And whose law is that?
If you have weight, what?
Same volume, same temperature, same number of moles.
Ideal gas law.
Ideal gas law, you would see that the pressure stays the same. Who Avogadro? Remember Avogadro's law? Right? You see little boxes, and you don't have the same mass of the gases, but you have the same mole. If the temperature is the same, and the volume is the same, and the number of moles are the same, then you have the same pressure as well. Right? Remember that? So that's important. So then if I have the same number of moles on the left side of the equilibrium and the right side, then do I have a pressure change if the volume is constant? No. So then I also have to, in order to determine if I'm going to add or take away pressure from a system, then the moles of the gases on each side cannot equal each other. Okay, that should make sense. Okay. Okay. And that's what the number of moles of gas reactants does not equal the number of moles of gas products. For that same reason, because then the pressure is irrelevant to an adjustment or a stress on the system. Because it won't do anything to the system, is what I'm saying, right? What would be that? So if I change the volume, let's say, if I had a piston and I pushed it in, and I had the same moles on each side, it's not going to shift or favor one side or the other of that equilibrium, because they're all the same number of moles, and therefore the pressure doesn't change from one side to the other. If I had different moles on each, then I would be the one that had more moles, right? That pressure would be greater on that side than the one that had less. And if I increase that, then the one that had less would then want more versus the other. It would change the ratio of the equilibrium of the reactants and the products if I had a different number of moles of each gas from each side. How would I figure out the mole? That's just the coefficient in front of the balanced chemical equation. So, if the pressure of a gas is increased by decreasing the volume at constant temperature, or decreased by increasing the volume at constant temperature, would create some level of change. So these are just words I want to get into, I want to show you what this really means. So you could read this. Let's skip through these kinds of things. This is something you could read. and let's see what it actually means when you're looking at this here. This is where it matters. Because this is the only time, all of those words, you can look back and make sure that you're right. But when you look here, is there a gas in this equilibrium equation?
Yes.
Yes. Okay, so pressure could matter here.
Yeah.
There's a gas on the right side, which means I have 1 mole of it. Is there a gas on the left side?
No.
No, so now the pressure definitely will matter.
Mhm.
If I apply pressure in some way to this system, what will happen is the question. If I apply pressure or I take pressure away, will it matter? The conditions are met that it would, being that I have a gas in here and that the amount of moles on one side and the other side are different. That means pressure can apply it. I can apply stress as pressure by taking away or adding it. If I take away pressure, what happens to the equilibrium? Will it shift towards the one that has the gas or away from it? If I take away pressure. So I increase the volume with the piston. I now have a greater volume, which means I've now decreased the pressure of the system. Which way will this adjust? Towards the thing that has the pressure or the gas, or away from it? I decreased the pressure. So that means that I will increase where the gas is. Because it wants to relieve that stress. If I added pressure to it, then it will relieve that pressure by losing some of the gas and going back towards the calcium carbonate area. Does that make sense? That's not as intuitive as the concentration one, right? All those things, that's why I didn't read off those slides. See, if I read those things, you'd say, yeah, that's great. And then I show it to you and you're still saying the same thing. Doesn't matter. You could read all that all you want until you actually see it and apply it is where you say, okay, now if we went back and said, these are those things that will make more sense, right? This slide should have come before those because now you can see I'm adding pressure here, then this already has more pressure than this. So if I add pressure to where there is more pressure, it will relieve it by going the other way. If I pull away the pressure from here where there's more of it, then it will relieve it by moving towards it. The same way as if I add or take away a concentration. And that's how Le Chatelier's principle would be applied if I added or took away pressure in an equilibrium system where pressure would make a difference. And that would be where there are gases on one side or the other, and there's more on one side than the other in terms of the moles. Okay. So one reacting species is a gas, that applies, and none over here, so they're not the same. So then I could say the stress, if I decrease the volume, so there's another way to state what I just said. I decrease the volume, I'm increasing the pressure. And this is where we looked at it. Therefore, it would shift the equilibrium away from where there already is more pressure. And that would be to the left.
Can we, instead of writing reverse or forward, just write where it's
You could write left or right, yes. But that means that this, you have to have this. What if I flip this? You have to have whatever it is you're referencing left or right from.
Yeah.
Because as an equilibrium, I could actually put this over here and that there, presumably. The only reason, why is it written this way? What's the assumption there? That it started at this and I didn't have any of that, and then I let the reaction go and it got to that equilibrium. That's the assumption. But once I'm at that equilibrium, doesn't matter which way I put what.
No.
Depends. Right? Whatever way you put it, you just got to make sure you're referencing that direction. Right? So a fairer way, in this case, it says this is increased, these are decreased, regardless of which direction it is. But if I have it as this is started and it went to these, then I can say it moved now from the right to the left. Would be a way, or reverse in this case. And then, of course, I increase the volume, I decrease the pressure, then it moves back forward towards where the gas was in this case. Okay, and there are my arrows. So let's take a look here. What about this? And of course, by the way, this is what I mean where I say we're in the section where we're looking at equilibrium, Le Chatelier's principle, and we're looking at pressure. It's not going to say that on the exam. It's just going to be, you're going to have one with ask about concentration, one that's going to ask about pressure. This is exactly what I mean by that. So it's easy to know here that we're talking about pressure, but you may not always know that. You have to read the question carefully and then decide how to apply it. So we already know we're talking about pressure here. So all reacting species are gases. I have 1 plus 3. I have 4 moles of gas here and 2 moles of gas there. Which one do I have a greater number of moles on?
On the reactant.
The left side.
Yeah, left
Okay.
side.
So let's establish that first. They don't equal each other, therefore pressure could play a role here, right? The equilibrium would shift if I applied a stress to it. So the stress here, pressure is increased. If I decrease the volume, that means I increase the pressure. Which way will this shift? I increase the pressure, so the side that had more pressure will want to be relieved.
Yeah.
And it will push it to the side that has less pressure, so it would go from left to right.
Right.
Which means I increase my ammonia and I decrease my nitrogen and hydrogen gases. That's it.
How do you know which side you should put the pressure or stress?
Whichever one is more moles.
Is it whichever one has more moles? Just more moles.
Let's see if I do that right.
Let me, now this is an interesting question.
But it depends what you want to do.
You're looking at this equation, what are you actually looking at?
A formation.
Where is it? Is it just floating around in the room? Are we talking about? Are we
Oh,
talking?
no, in a
How?
container.
What are we talking about here? Let's put big picture. What are we doing? It's in a container. The whole thing is in a container. In this fashion. The whole thing is sitting in a container. I have a piston on top. What did I do here? I increased the pressure, so I pushed that piston down. The whole thing is there. I'm looking at all 3 of those things in the container at the same time. By pushing the piston down, what is going to happen? It's going to force this equilibrium to readjust itself, and it's going to go from where the pressure is greater to where the pressure is less.
Right.
Does that help how I
It does help.
phrased it? So this now will become less in concentration. This will become more under all the same conditions, and that's all that's happening. So in the same container, you have all 3 things. That's the whole establishment of the equilibrium. It's in a container. And all I did was I adjusted that container in volume, which means that I've changed the pressure that's being applied to what's here, and that's now causing this whole thing to readjust and form a new equilibrium, and it will shift based on where you have less pressure going towards the less pressure as opposed to going towards more pressure, because I just applied pressure to the system. So I applied pressure to the stress is going to be more on the left side where there's a greater amount of pressure because there are more moles. So you have to look at this all within one container and how the whole thing is interacting based off of the conditions that surround it. So new equilibrium, these decrease, that increase.